Hello everybody, let's talk about this introduction to conservation of momentum using this toy over here, the Newton's Cradle. So Newton's Cradle is a popular desk toy that nicely demonstrates the law of conservation of momentum. Each swinging sphere collides elastically and transfers its momentum to the next sphere until one or several spheres emerge out the other side. You've probably seen one of these on someone's desk somewhere, or usually they're in gift shops. Use your understanding of momentum to correctly predict the outcome of the following combinations of moving spheres. Assume that each sphere has mass m, and that each moving sphere also has velocity v. The first one is done for you. Okay, so I have another video where I'm using this Newton's Cradle toy to actually show a bunch of combinations of, dropping in 2 spheres or dropping in 3 spheres or dropping in spheres from both sides at the same time. And in this activity, I'm asking you to figure out the physics of it, to use the patterns to determine the outcomes. So in this first one, we're looking at, this box is very important, right? It dictates the number of spheres that are moving in the collision, and it's just 1 to begin with. So before the collision, we've got 1 sphere moving to the right. It has a total momentum of 1 unit of momentum, right? 1 mass times velocity. After the collision, it moves this way, and therefore it would have a total of 1 mv after the collision. Okay, that's pretty straightforward. Moving to the right is going to be a positive momentum. Moving to the left is going to be negative momentum. So what happens if we go to, I'm going to try to erase this. What happens if we go to 2 moving spheres? Okay, how do we get 2 moving spheres to produce a total of -2 units of momentum? Well, that must look something like this. We must have, before the collision, 2 spheres dropping in and moving to the left, right? And hitting 3 that are at rest, okay? When they collide, then they will send 2 spheres out on the left side and leave 3 behind at rest. So these ones must be going this way. So we've got 2 units of momentum to the left here, and we've got 2 units of momentum to the left there. So the total momentum after the collision is also going to be -2 mv. Okay, let's increase the complexity a little bit more. What if we go to the next pattern, which is here? Still 2 moving spheres, but we need a total momentum before the collision of 0. Well, how is that possible? Remember that momentum has direction. So in order to get a total momentum of 0 while having things moving, their momenta must be canceling each other out. Like this. We must have 1 coming in, and I'm struggling to write here. We must have 1 coming in from the left, hitting 3 at rest, and then another one coming in, but from the right. Okay, so this has +1 units of momentum. This has -1 units of momentum, so that the total is 0. After the collision, they are going to pass through each other. So we'll have this one swinging out the other way, 3 at rest in the middle, this one going that way. So the total momentum after the collision is -1 mv from here, plus +1 mv from here. And the total is 0. Okay, I've done the first 3 for you, and I'm going to invite you to do the rest on your own. Pay attention to the number of moving spheres in each scenario, and then the total momentum that they have to add up to. Good luck.